I want to talk about solving equations a little bit first and then kind of graphing equations. And um, in this first section here in this book on 8.1, you'll see solving equations. And let me open this up a little bit more. And uh, they first are talking about single variable equations. So the idea here they're saying is that you try to get the variable isolated on the one side, and I have a tendency to always put it on the left. And you don't have to, but that's how I always do it. And then the base up number or something over here then on the right. So they take a look at an example here. We're going to get down to, and I'm going to do just some talking over the book a little bit here. And it says solve and check x minus 5 equal to 11. So we put up here x minus 5 equal to 11. Okay, so, and this is a pretty straightforward, single variable here, right? We start out, we have one variable, and we want to end up with just x by itself. So in other words, this 5 we want to get onto the other side. And if you remember, we're solving these to move stuff. You kind of have to do the opposite or inverse operation. This is a minus 5, so they say, well, you could take this and say this is x minus 5 plus 5 equal to 11 plus 5. Now I had to do the same thing to both sides of the equation, and if we do that, then things usually work out good. So the idea was here is I wanted to take at its opposite. So this negative 5 plus 5 went to 0. So I got just x over here, and this goes to 0. And I can add those. So 11 plus 5, 16. So then we would say that 16 is a solution to this equation up here, which is kind of open at the time. We don't know, it's not true or false. When we say it's a solution, it causes this equation to be a true statement. So if I put 16 in for x, so again we have x minus 5 equal 11, and then I put 16 in for x, so 16 minus 5 equal 11. So well, that's true, right? 16 minus 11. If we want to write out another step, we could say 11 equal to 11. So 16 again was a solution, and that's what we're looking for. We're looking for solutions. Now with single variable equations, if I wanted to graph the solution set, it's not very exciting. You'll see I could draw like a number line, and this would be like 0 in here, and we could have like, this would be like 5, 10, 15, and this would be negative 5, negative 10, negative 15, or something like that. So we're thinking of a number line. And so I have this number line without all this stuff on here. We usually just say, well, solution is 16, and it'd be like right there. So that one point, which is 16, right? That's a 16 place. That's my solution set. So graphing, in a sense, for these single variable equations doesn't seem to be necessary. I think that this doesn't help visualize, in this particular case, what we're working with, not much of an advantage. So we are going to clear this out and bring that back up. And we're going to move on here and not spend much time in here on these single variable equations, because again, we need to be able to solve them. Let's move this. And like, for example, here's another one. We say negative 9 equals a plus 6. And again, you can move the a over, or you could just say, well, let's get a by itself first. And that's what they do here. They say a plus 6, a minus 6. So let's see, 6 plus a negative 6 goes to 0. And that's what they're showing over here. This negative 9 was there already. And since we added negative 6 over here, we're going to add negative 6 over on this side of the equal sign. When I add these two together, two negatives, I add them, I get negative 15. And then a plus 0 is a. And we're left with this. And you can move these, this equal to this, same as this equal to this. So the direction that's commutative, how we write this final two terms here. So a equal to negative 15, we can write it like that. So negative 15 is a solution. That's that one point on the line, which we're not going to draw, right? So if I put negative 15 up here into the original equation, right, and for a, would that be true? Is negative 9 equal to negative 15 plus 6? And that's what they're showing here. Is negative 9 equal to, see a little question mark there. Negative 15 plus 6 is negative 9. So negative 9 equal negative 9. True statement. The negative 15 plugged into the original equation caused this to be a true statement. Okay, so that makes it a solution. And we're good on that. And again, we're focusing on the statistics more so than anything else. And this is going to lead us into something, right, we're going to do in statistics. So again, you can practice these and look at them and see if you have any questions on this stuff. But the single variable, again, one variable, we have basically one answer. And if we graphed it, it would be just like one point on a particular line, like an x-axis or a number line. And these is solution here, and then the check to see if it is true. So we're going to make sure we did it correctly. If we solve this incorrectly and say got r equal to 4/5, we forgot the negative. We said 4/5, and when we plugged 4/5 back in here, we would get 5/5 equal to negative. Nope, that wouldn't be true. So we would know we made a mistake when we tried to check to see if it ended up being a true statement. When it's not true, then well, it didn't work. Either we made a mistake or it just isn't a solution. All right, so let's go ahead and again, there's some more here to work with. And this is kind of like, a beginning algebra kind of thing where you solve single variable equations. And we're going to move past that. And again, these are some more simple single variable equations. And there's some other videos in the book. If you look at the videos of my stat lab, you'll be able to get lots of examples on how to solve these. Are all okay, same idea. So we're going to move on. And let's see, where is 8.2? And maybe I can jump to that page and let's see. So 315, let's go here. 315. There we go. So in this book, again, 8.2, Introduction to Graphing Lines. So this is not graphing what we just talked about in 8.1 with single variable equations. You'll notice, the one thing I want you to notice right away here, it says a graph of a linear equation in two variables. Okay, in two variables. Consists of all the points whose coordinates make the equation 2. Now this should say that we're looking for the ordered pairs of numbers. Okay, they're talking about x and y coordinates, but the ordered pairs that make the equation true. So we're not just going to try to find one number, right? We need two numbers, an x value and a y value in the Cartesian coordinate plane to come up with a solution. Okay, and let's take a look again. I'm going to put this down, and this is y equal to 3x plus 1. So let's take a look at this. All right, so this is a two variable equation because I have. All right, let's try that again. Y equal to 3x plus 1, or yeah. All right. So again, two variables. Here's my y, here's my x. So I got two variables, and now let's go ahead and see what we can come up with here and talk about this. Now y equal to 3 times 0 plus 1. So I just arbitrarily, you can pick any number you want. I put in 0 here, and I get y equal to, this is 3 times 0 is 0. I end up with 1. Okay. So what I'm going to do is over here, I'm going to say, okay, I make a table. And again, I can bring my ruler up here and make this line a little bit better. All right. Now, this is x. All right. I'm going to let that be x-axis. Remember we talked about this before. Y-axis. These kind of arrows are symbolizing this thing just keeps going on. And what I want to do is okay, let's take a look at that. Now, I'm going to come off to the side over here. And again, put table. All right. Okay, x and y, and I'll tell you why I'm doing this in just a minute. So over here, when I pick the number for x, I put 0 in for x. So I'm going to write that down over here, just kind of remind myself, right? 0 for x, and then I kind of worked this out here and came up with y equal to 1. All right, so that 1. So I have an ordered pair, and if you remember, if you have an ordered pair, you can actually graph that. So this is not going to be, this is 0 in the x direction and 1. So I'm going to write this right here, 0, 1 right here. All right, so that's my 1 point. And then I'm going to come back over to here and let's do that again. So I'm going to let x be equal to 1. I'm going to say 3 times 1 plus 1. 3 times 1 is 3, plus 1 is 4, so I get y equal to 4. Okay. So when I put 1 in for x, y was equal to 4. So I have this ordered pair of numbers again. 1 comma 4. All right. So I have 0, 1. Just to remind me, that's the point 0, 1. This is 1, 4. And let's do one more. Let's do -1 in for x. All right. So 3 times -1 plus 1. 3 times -1 is -3 plus 1 is going to give me a -2. Y is -2. So when x is -1, y is -2. Okay. So -1, -2, I can plot. I can go -1, -2. And this type of equation is what we call linear equation. Okay, if you remember, we were talking about correlation. Correlation, there's lots of different types of correlation. You can have linear and non-linear, you can have exponential and quadratic and cubic and all kind of different kinds of. But for this course, we're focusing on linear correlation. So we're trying to tie in a linear equation with that linear correlation. And remember that those are things that we talked about with linear correlation still all hold true and relate to kind of a more, this is like an algebraic approach right now. And so I'm going to bring this thing over, draw my line through there. Okay. All right. So this line goes on and on too. Also, I got the arrows here. Now, so it's a straight line, right? Straight line. And that's kind of what we're shooting for here. These equations in this section in your book, we're going to focus on ones that are kind of this form here, where you got the y equal to something times x plus something. Now, they don't have to be in that form. We could move stuff around, but I don't want to focus on equation solving. In this course, again, we're kind of more focusing on the statistics part of it. So this is really our kind of goal right here, right now, is being able to see a two-variable equation, plug some values in, get some ordered pairs, right? And right now, we're just drawing a line here, right? Okay, good. All right, so let's look at here we got the ordered pair. We got the table for the x and the y values. And you'll see, here's their graph. They picked 0, 1, they got 1, 4. They picked another one way up there. Oh, there's our -1, -2 that we had plotted. They plotted 4 points, we plotted 3. Okay, so let's go to here's another example. And one thing they said that you can do also is you can find the slope of that line. Well, we talked about slope, right? We talked about positive slope and negative slope and zero slope and undefined slope. So we're just going to kind of review that real quickly again. So here's our formula for slope. Remember, y sub 2 minus y sub 1, x sub 2 minus x sub 1. And I don't want to, again, since this is on the other video, I'm not going to spend a lot of time on this video on it. If you forgot, you go back and review the other one. But they took 2 points from that line that we had. They took the 0, 1, and the 1, 4. Okay, 0, 1, and the 1, 4. They use these two ordered pairs. And remember, it doesn't matter which one you call y1, y2. They're looking like this is the 1 and 0. They're saying that's the second point right there. And that's okay. As long as you remember x, y. X goes in the denominator. The y goes in the numerator. 0, 1, and then 1, 4. That's my y values, x and y values here. We subtract, we get -3 over -1, and there's my slope of that line. So this line here has a slope of 3, right? Oops. There we go. Okay. So let's go ahead and forward on this. And again, graph the equation. Now this doesn't have the x and y. It has the x and y on the same side, and that's okay. There's nothing wrong with that. But for what we're doing, we want to solve this thing for y. So in other words, this 2x, we're going to move over to the other side. And you'll see here what they did. So the 2x, they subtracted 2x from both sides of the equation. In essence, they move this term here onto the other side, and they get y equal to -2x plus 3. So they're showing their table, y equal -2x plus 3. And then they plug in -1 and get 5. They plug in 0. So the same thing. They go through and find 3 ordered pairs. And they plot those 3 points, right? Find the slope of the line by using any 2 points. So they chose these two to find the slope. And the slope of the line remains consistent. So that's why you can choose any 2 points on the line. So that's the only function, linear one, is when the slope stays the same on a straight line, right? So, and then they talk about 2 other points here, x-intercept and y-intercept. And again, I'm not going to focus a lot on these, but the intercepts we talked about, and that's if there's a point right on the axis. So on this x-axis here, you see there is a point right there, and it looks like it's about 1.5. And then there's a point on this y-axis. It's right at 0,3, right? So you can go through and find those by plugging zeros in for the equation here, okay? So let's go ahead, and we're going to go ahead and do that since I haven't done that yet. All right, so remember our equation was 2x plus y equal to 3. And the first thing that they did is, and you don't have to do this, but what they did is they said, well, let's go ahead and move this over to the other side. Now, if we wanted to find the x-intercepts, if we wanted to find out where on the axis, x and y axis, there was a point, you could leave it like this. And what you could do is you could start out and say 2 times 0 plus y equal to 3. That's 0. And you get y equal to 3. So we have this ordered pair. X is 0, y is 3. Okay. So on a graph, then when x is 0, y is at 3. Okay, and again, I'm just going to draw a quick graph here. So 0, 1, 2, 3. Okay, so this is my y-intercept. Sometimes people call them zeros because that's what you're working with, 0. When x is 0, you find your y-intercept, right? So let's go ahead back here and erase this. Now, we have the y-intercept. Let's find the x-intercept. So 2 times x plus 0 equal to 3. So 2 times, well, that's 0, so we get 2 times x equal to 3. Divide both sides by 2. We get x equal to 3 over 2. When I divide this by 2 over 2, I get 1, so there's 1x. And when I divide 3 over 2, I get 3 over 2. So when y is 0, x is 3/2. That's my x-intercept. Okay. So these are points. These are some special points. They're good to know. That's a good thing to know. And we use it in statistics. We like those points, just like they do in algebra. Let's graph this thing. 3/2, comma 0. So 3/2. Go out to the right from the origin, comma. I don't go up or down. My y is 0. So, and I could graph this thing, right? I could come up with a, let's see if we can get this up there. All right, so let's draw a line right through those. And so we have 2 points. We can draw the straight line. And so our line, you notice this is a negative slope, right? So there's a negative slope. And again, we could use these 2 points. We have m equal to, and let's say that this is the first point we're going to use in that slope formula, right? So remember 0 and 3. So here's this x is 0, y is 3. So put that there. And then minus, minus. Okay. Now, x is 3/2, right? And this is 0, right? So we got, again, the first point, x, y goes in the numerator, x denominator. My next point, I'm going to put in x in denominator. So this is equal to 3 minus 0 is 3, all divided by negative 3/2. Division by fractions, the same as multiplying. So we got 3 times negative 2/3, right? And then when we multiply those fractions out, right, this and this is 1, so I'll make negative 2, right? So my slope of this line is negative 2. All right, so let's go back in and take a look at this. And okay. Oh, let's go ahead to the next page. And again, here they're showing the intercepts in the graph. And they got the substitutes. We're just going to go ahead and move on. So they say that to graph a line, again, this is more of an algebra, not so-called statistics, but we still need this. You'll see we'll tie this together. And we can plot some points. Now, if you want to find the intercepts to plot the points, then great for all, and your lines, you can get those. And unless it's going straight up and down or straight across, right? You got some special cases with a slope of 0 or a slope undefined. But all the other cases, we're going to cross somewhere. We can find those intercepts, so we don't only have 2 points, we also have the 2 points we can draw the line then, and we can also use those 2 points to find the slope, and then also we have our intercepts. So it's kind of a good thing, if possible, just go ahead and find the intercepts and you can get a lot. And now here's our special case. Remember, we did one of these. We said that it is possible that you can have a slope of 0. This is straight across. And if we use the slope formula, we would still graph it the same. We would graph, here's -6, 9, -2, 9, 3, 9, 5, 9. So see all those points have the same y value. Y equal to 9. That would be the equation of our line. Y equal to 9, because that's the good way to describe that thing. It's a special case. So we're just going to leave it at that. And here's our other special case. If you notice, all these points on this line going straight up and down have -5.8, -5.8, -5.8. X is equal to -5.8. That's our equation of the line. X is equal to -5.8. Special case, that's all we have. There's no 2 variables in this equation here. We don't need it. We just need the 1, and it defines that clearly, okay? And slope is undefined. Okay. And again, same idea. You have a line in this first quadrant, no matter what it's dealing. Here we have number of movies ordered, monthly bill. They didn't have any movies ordered, they paid $30. They had 10, right? 10 movies ordered. The bill was $80. And then 20 movies, well, $130 then for the bill, okay? Those are ordered pairs. Plug them in, get your values, right? And we are on 322. And let's go down here. So if we have something in this form, they're calling it the slope-intercept form. We got the y on the left and the m and x plus b. So the m is just a general parameter. X, the y and the x are our 2 variables. The m is standing for the slope. See here, m is the slope, and b is the y-intercept. So it's what we want for the statistics of what we're going to talk about. So we were looking at that, and they say, well, if it's in that form, things are kind of nice. Here we have y equal 3x minus 5. So I know the slope is 3 because it's in this form where you have y, the x term here, and then a constant. The number in front of the x is the slope, not the 3x. 3x is not the slope, just the 3 is the slope. So these is the slope, that'd be 3. Okay. So they say if it's not in that form, well, you could change it into that form. Move the 3x over, divide by 5. You can see the work here. So y is equal to -3x plus 6/5. That means that the slope is -3/5. The y-intercept is 6/5. What's that mean? That means that there's a point on our line, right? Our solution set that is 0,6/5, right? There's a point sitting on the y-axis at 6/5. So here's our equation again. And what they're saying is you can kind of play around with this. And if you're given the slope and the y-intercept, you could write the equation y equal to -4/5 x minus 3. So here they just write that out. Here's my slope intercept, right? Here's the slope. Here's my y-intercept form of the equation of a line. So it's a linear equation. There's several different forms of linear equations. The one that's going to suit us the best in statistics is slope-intercept form. That's the only one we're going to talk about. We don't really care about the other forms, right, for what we're doing. Again, here's a graph, it says. Well, you could plot some points. You could find the intercepts. You notice right away they put in 0 for x because it's easy, right? If you put in 0 for x, you get 2. So 0, 2, they put that there. And they say, well, you could use the slope to help you find it, but I suggest that you just find the other intercept, and that would be the easiest way to do that. So again, I'm not going to spend the majority of the time on that. We want to go to 346. Okay, so 8.3, linear modeling. It's the exact same things we were just doing, okay? Linear functions, it just means that what we were doing, same thing. We have a relationship between two variables, and we're assuming that the relationship is a straight line. If we plotted all the points that satisfied the equation, all the ordered pairs of numbers that satisfied it, we would have a straight line like this here. So here we're saying time and rain depth. So you can see after 1 hour, it looks like it's about 1. 2 hours, it's about 2. 3 hours, it's about 3. So there's a slope here of 1. 1 unit this way, 1 unit up. So it's a 1-to-1 kind of relationship there. They refer to that as rate of change. So how much did the y value change with respect to 1 unit of change in the x direction? Okay, so that's another way to talk about slope. Here's some different slopes. Those are positive slopes, remember? They're going up. And they have different rates of change. This is a 0.5 inches per hour. So that means when you go 1 hour this way, it goes up half an inch. 1 hour this way, it goes up another half of an inch, so we're at 2.1 then, and so on. This has a 1.5 inches per hour. So you go an hour, you're up at 1.5. You go 2 hours, you're up at 3. 3 hours, you're up at 3 times 1.5, up at 4, and so on. You notice the y-intercept here is at 0. The x and y-intercepts are right at 0. All right, so rate of change again is the slope. Right, so. And here's a price / demand. Price of pineapples, demand. So this is a negative slope. Right? And what we mean by negative is that as the price increases, people are going to want less of that product. So as price goes up, demand goes down. As price goes up, we sell less pineapples. Okay. So at 0, well, it's 100. At 1, it's down here. It moved down. Let's see if we can get to 2. Well, it looks like it's saying it's 2,80. Okay, right there. So if we sell them for $5, well, we only sold 50 pineapples. So we definitely sold less, right? Sold less. So that's a negative relationship there. Rate of change, again, slope. We've done slope. Okay, we're going to keep moving here. Rate of change, right? Change in the dependent variable. Rate of change times change in the independent variable. So they're basically saying that as we move in again, 1 unit of x direction, we have slope units of change in the y direction, right? That's our rate of change kind of rule, how we're going to talk about it in statistics. So you don't have to remember that formula for anything. General equation of a linear function, again, we're not going to look at that. And let's look at this here. So on page 351. Now, these are pretty important. We see this, dependent variable, independent variable, initial value, and rate of change. Okay, so let's look at these examples here. And so the independent variable is the x-axis variable. Okay? The dependent variable is the y-axis variable. Okay. Now, the initial value is when x is 0. Okay. When x is 0. And then the rate of change is the slope. Okay, it's the slope. And they talk about some different functions. There's a linear function, linear relationship for blood alcohol. Again, you don't have to memorize any of that. We just want to look at the function here. Okay. So the independent variable is time. Here's our x-axis, time. Dependent variable, blood alcohol concentration. The initial value is when, in this case, t, time is 0. It was way up here at 0.08. So after this person had, so much alcohol in their system, at time 0, when they stopped drinking, they would have like 0.08. And then as time went on, the alcohol concentration drops. So after 1 hour, it was down, and then it went down 2 hours to 0.06. After 6 hours, blood alcohol concentration is at 0. Okay, so it took 6 hours for all that to get out of the system, right? If we wanted to find slope, we would have to get a couple points here, right? Here's one point is 6, 0. The other point is 0, 0.08, right? And we are on 354. And again, they review the slope, right? Change in the y's over change in x. So, and one thing we can do too is you'll notice here, they show the red line shows a linear model for the 2 data points. The blue curve fits the data with an exponential function. So we're only talking about linear, right? They're saying, you know what, there could be lots of different types of curves going through 2 points. And yes, that is true. So that means we got to plot more than 2 points. If we get a set of data values, we have a bunch of ordered pairs, we're going to plot, right, and look at a scatter plot. So remember that. We'll be getting back into that in the next video. So we're going to get into what we refer to as regression. And regression is simply, having a bunch of those points all scattered about and then finding a line that fits those points the best. And so we'll be getting to that. So we're going to stop here and then look at regression again and finish up this chapter 8 on the next video.